Hello everybody out there in YouTube land. This is Good Times for All, or Zachary Zabali here if you prefer. I just wanted to make a quick video um, discussing some of the things that I found. I'm definitely not done researching. There's still definitely more I need to find, but I've been racking my brain on this, and I figure if I just throw it out there, especially with what I found, maybe some other people will jump onto it, and I can find some more people to bounce ideas off of and stuff like that. But what I've been looking into is called Rayleigh's criterion, or the angular resolution limit, which means that, okay, at your horizon line, there, take a straight line from the middle of your eye, or the middle of your lens, whatever you want to say, the center of your aperture, and if you just go straight out, horizontal, that's the horizon. That's your horizon line. No matter how high you go or how low you go, your horizon is at eye level. I don't care what the trolls say. Show me a scientific document that says that the horizon dips down once you get so high, because I haven't seen it. So, okay, the horizon is at eye level. All right. Now, your angular resolution limit is for so many degrees up and down along that horizon line. Once an object gets so close together, your every lens and aperture, any size lens, it doesn't matter, has one of these. This is a fundamental limitation of physics. This isn't, maybe it does it, maybe it doesn't. This is a fundamental law of physics. Every lens with a certain size aperture has a diffraction limit that it cannot see two objects. Once they get so close together, they blur. That's your angular resolution limit. And you find this using Rayleigh's criterion. And there's all kinds of extra math that I'm looking into on it, and I think I found out how to add in the atmosphere, but it's for astronomical observations, and I want to do terrestrial observations. Now, we could be like the geodetic surveyors and just throw it down in there and say, oh, it can't be much different. But I want to do it legitimately, and because I want to know the truth. But we won't get too much more into that. So anyway, angular resolution limit. Now, for the human eye at 20 feet with your pupil, which is your aperture, at the size of 5 millimeters, the average human eye has an angular resolution limit of 0.02 degrees. So along your horizon line, for 0.01 degree up and 0.01 degree down, you would not be able to make out anything that small. I think it's 2 millimeters. Anything closer than 2 millimeters, and you would not be able to see it if you had 20/20 visions at 20 feet, 21 feet, something like that. So I did some calculations using that, and I realized that that is with a 5 millimeter open pupil. Now, if you're looking at something 10 miles away, or even 3 miles away, just to the horizon, your pupil gets much smaller as you're focusing in on something. You'll even squint your eyes. And what you're doing is you're blocking out all the light from the outside sources, and you're just trying to focus in on that one object. That's what's happening when you do that. Now, when you do that, in the Rayleigh's criterion, your pupil diameter, or your diameter of your aperture, is a big part of that. So if your diameter gets smaller, that means your angle of resolution limit actually gets bigger. So say you're at the beach and you're looking at something 10 miles away, and you're squinting at it trying to see it, your pupil can get to about 2 millimeters. Okay, so that would make it 0.038, I believe, 0.038 degrees would be your limit of angular resolution. And that would come out to be, I wrote it down, 34.86 feet. And that's just at 10 miles. Now this is with the human eye, not with the camera. With camera it changes. You have to, there's mathematical equations to do it all. It's not that difficult. But anyway, so now that would be 34 feet, so it'd be like 17.4 feet above your horizon line and 17.4 feet below. So if you're 17 feet above the water looking out over it, that means 34 feet, all 34 feet would be blocked out at 10 miles away. Not at 5 miles. It'd have to go all the way back to 10 miles, but for that 0.038 degrees right there along the horizon, you will not be able to make out anything closer than that. And then the further away it goes, the bigger the amount of feet would get, of course, because it's all based on angles. So that's just at 10, and that's with no atmospheric conditions affecting anything at all. Which also, when you start throwing in the atmosphere, that makes your diameter even smaller. And it can cut it in half, the atmosphere. It can cut it down to where you can't even see 50 yards in front of your face if there's so much fog. And they have scales for all of this stuff. Astronomers use it. I'm trying to find it for something for terrestrial viewing, and I just found the astronomer thing yesterday or the day before. It's called astronomical seeing. It's what makes stars twinkle and dance. When there's, they say it's not so much caused by heat, but just the circulation of the air, the fluidity of the air moving around up there. And it can cause all kinds of disturbances, turbulence in the ether that you're trying to look through. And this also happens at ground level even more because the air is denser and thicker. So still a lot more research to do, but I just wanted to try and I want to throw this out there so other people might start thinking about it. But that's it. So, but one more thing real quick. You have to add this after your curvature calculator. So all the curvature calculators, when they say, okay, at 10 miles, blah, 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 at 5 feet up, you have 35 feet missing of the shore. Okay, that's great. Now add, depending on your height, at least 17 feet. And that's if you're at sea level. So if you're at 5 feet up, it'd be 22 feet more that you would have to automatically. Fundamental laws of physics. Fundamental. Cannot be, there is no way around it. You are not going to be able to make out objects within that 22 feet there. So from the ground, from the water level up 22 feet up, you will not be able to see that. So you have to add that on after you take on the curvature calculator. So there should be even more hidden than they're telling us. Sorry about that, folks. My storage ran out of my phone there for a second. But anyway, this will be needed to be added to the curvature calculator there. So at 10 miles, 5 feet off the ground, 35 feet of curvature should be blocking the bottom to the next side. Now you're going to have to add 17 feet up and then the 5 feet down. So 22 more feet, making it 57 feet. Not 35 you shouldn't see from across there, but 57 feet. So I mean, this is a game changer, I believe. So at any distance, you're going to have to find out the angular resolution limit for your camera, which isn't hard to do, and add that on to how much after the curve. So this is just going to make it even more ridiculous of how much we can actually see. But that's it, folks. I don't know. That's it. So if you have any ideas or anything like that, get back to me. But this is Good Times for All signing out. As always, thanks for watching.